Hi everybody, this is Jeremy, and today what I'm going to do is go through the 3 examples that I did in class for mathematical induction. While we have a great deal of proof techniques available to us in mathematics, a common one and a very rigid one is proof by induction. It's one of the few cases where you can say these are the steps to the proof. Now, of course, there's contrapositive and proof by contradiction where there's a general idea of the steps, but here, again, it's much more clear. We're always going to prove some basis step. Now, some textbooks would tell you this would be P of 0, but for us, we're going to use P of 1. And then we want to prove that for every k, you can prove that if the property is true for k, that it has to be true for k plus 1. So that's what that notation means. P of k means the property is true for k, and P of k plus 1 means property is true for k plus 1. So what we'll do in our proof, the general outline will be prove that it works when you plug in 1. Usually it's a really silly, quick step. And then say, okay, now assume it works for k. Do some kind of magic, show that it has to work for k plus 1. Now, I said do some kind of magic, right? Often that's going to be some kind of algebraic magic, factoring, multiplying. Maybe we wouldn't call that magic, but simple algebraic steps. Other times, though, it will be a little tricky. There'll be some kind of algebra step you need to show that the formula works in the way that you expect it to work. So here's my first example of a proof. We want to show if n is a positive integer, then this formula is true, a very famous formula actually for adding up all the positive integers up to n. So before we even get started, let's think about what the work would be. What do we need to show? What do we need to do? So I'm going to put a little scratch work thing over here. Okay, so we're going to show it for 1. That'll be an easy case. We just plug in 1. But let's think about the next step. On the second step, what we're going to do is assume it's true for P of k. Assume P of k is true. So in other words, we're going to assume that 1 plus 2 plus ... plus, add up all the numbers up to k, and that you'll get k times k plus 1 over 2. Okay, so that's the P of k. We want to show that if that's true, that when you add all the numbers up to k plus 1, so k plus 1 would be the next number right after k, that you end up with the formula working for k plus 1. Now, what happens when I plug k plus 1 into this formula? Well, I have k plus 1 times k plus 1 plus 1 over 2. And simplifying that a little bit, that equals k plus 1 times k plus 2 over 2. Now notice how meticulous I am about this. Right over here, I could have written k plus 2 automatically when I was plugging in the formula. I see it's going to be k plus 2. But I do this so I can see where it's coming from, because it might give me hints in case I get stuck writing the proof. So again, our steps are going to be write the proof for the basis step. That'll usually just be an observation that it works. Then assume this and go to this. So how you write that is really a style thing, but I'll give you an idea by writing this out formally now. So I'm going to do a proof, let everybody know it's by induction, although most people would recognize that if they study a lot of mathematics, it's a nice thing to do. And so now what I want to do is start out my typing. So I say, okay, note that for n equal 1, and now I want to show that it works for 1. So for n equals 1, we end up with 1 equal to 1 times 1 plus 1 over 2. And so if you look at this, you get it. It's true. For n equals 1, this is true, so we're good. We don't really have to say that. We could say, note that for n equals 1, blah, 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 so the formula is true. But I tend to be more short in my proofs. Okay, so now what we want to do is start writing the real part of the proof. So I say, okay, so suppose the formula works for for n equal k. That is, we want to say that 1 plus ... plus k equals k times k plus 1 over 2. Okay, so if we assume that that's true, remember our goal is to show that this is true. So I want to do something to make this work. You notice the only difference on the left-hand side, for example, is that we have this k plus 1 over there, right? And so what I'm hoping is when I add k plus 1 to both sides, that I can simplify and it will come out like this. So basically I try to make the left-hand side look like I need it to look, and hoping the right-hand side works itself out. Typically, I would do this as part of scratch work, but I'm limited for space here, so I'm doing it as part of the problem. So, okay, so I would say then, and say what we're going to do, we're going to add k plus 1 to both sides. And so let's see what happens when I do that. So adding k plus 1 to both sides, well, let's see, I end up with 1 plus blah, 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 k like I had here, and then I'm going to add my k plus 1. And then this equals k times k plus 1 over 2. We already know that because I'm using this formula. I'm keeping this. And now I'm going to add k plus 1. And so what we want to show is that this, which I have on the left-hand side, I have it right here, is equal to this, which right now it doesn't look like I have, but that's my ultimate goal, is to show that actually this is that. And so what I'll do is start trying to simplify. This is equal to k times k plus 1. And then if I multiply by 2 over 2, I can add these two fractions, or add this to the fraction. And then at this stage, you can either be really slick and notice something, or not so slick and not notice it. The first time I did this proof, I have to say I didn't notice it, and so I multiplied through. I got a quadratic, and it factored perfectly exactly what I wanted. But now I'm looking at it a third time probably, and I'm looking at this and I'm seeing, I could just factor out a k plus 1. If I factor out k plus 1, what am I left with? K plus 2. Way easier than having to multiply. But notice I get here, either way would work. So sometimes your steps might look a little bit different. Now at this stage, a lot of people would end the proof. Anybody who knows induction has read it. They see that you did the basis step. They see you assumed it's true for k, and then you showed it was true for k plus 1. But you could also type it out. And so let me show you how that would look. And this is totally up to you if you want to do this or not. But if you wanted to do this, you would say something like, since the formula is true for n equals 1, and if it is assumed true for n equals k, it can be shown it is true for n equals k plus 1, which we did. Then by induction, the formula can be assumed true for all positive integers. And that would be the end of my proof. Now I have to say I'm probably never going to type that out again writing one of these proofs, but you'll see it written sometimes. As you get more comfortable, you'll probably notice your proofs get a little bit more short. And so a lot of this work you do on the side, and you see how algebraically you're going to do it, and then you write up a nice proof like this. So let's take a look at another one that's very similar, and then one that is not as similar, and so that you can get the general idea and the pattern of induction. So in this problem, I'm asked to prove a very similar formula. It says if you take each number up to n, each positive integer, and square it and then add them up, that you can find the sum using this formula. So the procedure is going to be very, very similar. As you'll see, the thing that changes is usually just the algebra to get there. So let's figure out what we're going to do. We know we're going to do the basis step. That'll be the easy step. I want to think about the next step and see if I see anything obvious. So after I prove the basis step, I'm going to assume that this is true for k. Now, often we just say k, and it's understood you're talking about a positive integer k. Now, depending on if you're taking my class or somebody else's class, they may say, hey, you should say what k is. So maybe we'll add that into this proof just so you can see what it looks like when we add it in. But it's usually with induction, it's understood that you're in the same set that you are working with. So, all right, we're going to assume that this works for a positive integer k. In other words, if you were to square all the numbers up to k and add them up, that the formula will give you the correct answer. So we'll get 2k plus 1 times k plus 1 times k over 6. And now we want to show that the formula works for k plus 1. So we want to show if you add up all the squared integers up to k plus 1, positive square integers, of course, that you end up with this formula with k plus 1 plugged in. So you get 2 times k plus 1 times k plus 1 plus 1 times k plus 1. Now, it may seem silly that I don't simplify as I go, but I like to have this to look back on as I'm working. Okay, and then here we get 2k plus 2 plus 1, so plus 3, times k plus 2 times k plus 1. So unless I see something really interesting as I'm doing this, I usually assume that I can do the trick I did last time, add the k plus 1 squared, the term that I need to both sides, do some algebra, and end up with this formula that I want. If I see something as I'm working on this that could lead to a trick, I pay attention to it, but that honestly doesn't happen that much, and especially not in when you're first learning induction. Okay, so now I kind of have a plan. If I want, what I would typically do is I'd continue scratch work to see if I can get from here to here. But since this is for a video and I know that it's going to work, we'll just jump right into the proof. But that's what I would advise, is kind of playing with the algebra first. Don't put a bunch of ugly algebra that doesn't work in your proof. Save that for scratch paper and then write yourself a really nice proof. Okay, so by induction. So the first thing I want to note is that for n equals 1, that the formula works. So in other words, we end up with 1 squared, which is 1, equals 2 times 1 plus 1 times 2, 1 plus 1 times 1 over 6. Right? And so let's make sure that we're not doing something silly, proving something we can't. We get 3 times 2, which is 6 over 6, which is 1. I don't need to explain that that's the case. It's obvious when you look at it, but I want to do this basis case, like, hey, the formula works for this. All right, so like I mentioned, it would be nice to go ahead and state what k is, right, if we're dealing with positive integers. So I would say, now assume that for some positive integer k, the formula works. In other words, for some positive integer k, 1 squared plus ... plus k squared equals, and now I plug in the k, 2 times k plus 1 times k plus 1 times k over 6. Right? And so this is now this step. I've assumed this. That's p of k. So now I want to prove p of k plus 1. Right? So now I want to tell people what I'm doing. Some people may ask, why do I say what I'm going to do? I think it helps the proof read nicer. So now I'm going to say, adding k plus 1 squared to both sides and now I know I left off the squared there, but that's more a technology thing. It's easier to write in. There we go. Adding k plus 1 squared to both sides. Now, why would I do that? Because I want to show this, and the left-hand side has a k plus 1 squared added to it. So the goal is to make this look like this. That's my first step, is get the left-hand side to look like it, hoping that the right-hand side falls into place. So this will be 1 squared plus ... plus k squared plus k plus 1 squared equals all this plus k plus 1 squared. All right, so before you go crazy trying to multiply things out, see if there's a way to avoid it. I say this from experience. In fact, with this very problem, I jumped straight into trying to multiply things out and it got ugly quick. Not that we can't all handle easy algebra and factoring and everything, but why go through all the kinds of ugly algebra I saw when you don't have to? So that's why I recommend doing the scratch work and then writing your proof so it looks like you found the slick method first. What I'm going to do is I'm going to multiply this by 6 over 6 and combine the two fractions, or combine this fraction and that. So 2k plus 1 plus 1k plus 1 times k, and then we got plus 6 times this, and then all of it's over 6. Okay, here's where I started going crazy and multiplying. Please don't do that. Observe k plus 1's in these two terms. So factor it out. When you factor it out, you get left with 2k plus 1. So I think this inspired me to do that on the previous problem as well, times k, and then you're still left with a k plus 1. All right, this may seem like it didn't help you much, but now when you multiply this, you're ending up with a quadratic, which are much easier to deal with than cubics or even things with fourth powers. So we get k plus 1 times, and when you multiply this out and simplify, you end up with 2k squared plus 7k plus 6. And this is all over 6. Right? And so now, luckily this factors, and that's what I was most worried about that it wouldn't. When I first saw that, I was so excited. You get 2k plus 3 times k plus 2, which is exactly what I needed over here. As you see, I was able to get it to look like what I wanted to. So I was able to show that this equals this, which is exactly what my want to show was. So we could write a sentence like before, but in the interest of showing you different styles of these proofs, a lot of people would end the proof here. So I can put this little box and say, hey, I'm done, or a QED or something and say, hey, that's it. If you know induction, you know I proved it. I assumed it was true for k, I showed it was true for k plus 1. Or again, you could write a nice sentence concluding it. And if you're taking discrete with somebody or taking a class where you need to write one of these proofs, pay attention to what your professor would prefer, of course, because it depends on them a lot of times too when you're first learning, because sometimes they have certain ideas they want to hit several times. So you can see the first two are similar. This one, the algebra gets messy if you don't see the quote-unquote trick of factoring out the k plus 1. So I want to show you a problem where it's not as just messing with rational expressions, not messing with algebra so much as, well, it is a little bit, but it's just a little bit different. So let's take a look at one last example. So this one says, n's a positive integer, prove that 4n minus 1 is divisible by 3. So you see it doesn't look anything like what we've been doing. So we're going to use induction for this, but the steps are still going to be the same. We're going to prove when you plug in 1 for n that you get a number divisible by 3. That'll be the basis step. That'll be easy step. And then we're going to prove that if you assume it's true for k, it's true for k plus 1. So let's write down our goals here. So at that stage, we're going to assume that 4 to the k minus 1 is divisible by 3. Okay, think about what divisible by 3 means. That means it's a multiple of 3. So that means that 4k minus 1 is equal to 3 times something. So we could say 3 times a for some integer a. Now, certainly if we introduce an integer other than k in this, we need to make it clear what it is and that it's an integer. We want to show, now we're going to put k plus 1 in there, that 4k plus 1 minus 1 is divisible by 3. That means, again, same thing, that 4 to the k plus 1 minus 1 equals 3 times something else. It doesn't have to be the same thing, where b is an integer. Right? So our goal is to go from here to here. Very different than what we did before. But there's definitely going to be a way to do this. So again, we want to show that it's a multiple of 3. That's the same thing as showing it's divisible by 3. So I'll do my proof just like I've been doing. And again, I advise working on this on scratch paper and then writing up your nice proof. So we'll say, okay, we're going by induction. And so I feel like being a little obnoxious with my introduction. So you're allowed to do that, of course. I'm going to say, of course, if n equals 1, 4 to the n minus 1, we get that 4 minus 1 equals 3, and that is divisible by 3. So of course it works for n equals 1. Obviously we're done with that part, right? So now we're going to assume that it's true for k. So I'll add in the exponent in a second. And so I want to say now assume that 4 to the k minus 1 is divisible by 3. So that means for some a equal to, for some integer a, let's say, that 4 to the k minus 1 equals 3a. By definition, we don't have to really explain that at all. All right, so somehow we want to get to this. I think I need a little more scratch work, honestly. So I want to get to 4k plus 1 minus 1, the minus 1's down here, is equal to 3 times something. But I want to remind you that 4k plus 1 equals 4 times 4 to the k, right? Because remember, you add exponents. This is like a 1, so it'd be 1 plus k. So really, this is after I've multiplied by 4. So to get from 4 to the k, oops, and this should be a minus 1 here. to get to the 4 to the k plus 1, I need to multiply that by 4, right? So I need to multiply by 4. Why don't I just see what happens when I do that? Now, that would typically be for scratch work, but since I know it's going to work, I'm going to do that. So I'm going to multiply by 4, and I'm going to tell my readers that that's what I'm doing. So I'm going to say, okay, multiplying by 4. What happens? So we end up with 4 times 4 to the k minus 1. You got to remember to write it like this. Equals 4 times 3a. All right, so this will simplify to 4 to the k plus 1, multiplying these two, minus 4, because it distributes, equals 12a. All right, it made it look like I don't quite have what I want because, okay, 12a is 3 times something. So we're pretty good, but this is a minus 4. That's not good. I want that to be a minus 1, right? Look at my 1 to show. I want that to be a minus 1. So I could just add 3 to both sides, right? You can do that to an equation. All right, and now notice what I can do. This equals, I can factor out a 3. 3 times 4a plus 1. So now I can say something to kind of organize it. I could say something like if b equals, or if we let b equal 4a plus 1, then b is an integer, and 4k plus 1 minus 1 equals 3b. This means that it's divisible by definition. And so we're done. So I want to write that up kind of nice. So by definition, this is divisible by 3. And that would be the end of my proof. So this one is maybe a little more intuitive, not as obvious as the other two, a little more difficult. I had to do a lot more writing instead of math, but it's the same idea. This is also a proof by induction. And so you want to pay attention to the different types of proofs. Get really good at the ones like we saw before that are just formulaic, and then start learning how to work with these where you're still following the same pattern, but maybe to get there would be a little bit different.